Today we are going to discuss about Unit 2 switched reluctance motor. So the contents which we are going to discuss in Unit 2 are steady state performance prediction by analytical method, torque speed characteristics, methods of rotor position sensing. Now this is a switched reluctance motor in which we have the stator which is slotted to accommodate the armature conductors, whereas the rotor is in the inner portion. There is a flow of flux lines from the stator to the rotor, and we have marked the flux paths as 1, 2, 3, 4, 5, 6, 7, etc. An SRM with a 8/6 pole combination is considered for deriving the analytical procedure for inductance evaluation. Assume a certain flux density in the stator pole and the flux densities in the other parts of the machine, such as rotor pole, rotor back iron, stator yoke, and air gap, are derived as the areas of cross section of these parts for assumed flux paths are obtained from the machine geometry and the assumed stator pole flux density. From the flux densities in the various parts of machine and the flux density versus the magnetic field intensity, that is BH characteristics of the lamination material, the corresponding magnetic field intensities are obtained. Given the magnetic field intensities and the length of the flux path in each part, their product gives the magnetomotive force, that is H into L. It's nothing but the magnetomotive force. The MMFs for various parts are likewise obtained, and for the magnetic equivalent circuit and the stator excitation, Ampere circuital law is applied. If an error between the applied stator MMF and that equivalently by various parts of the machine reveals a discrepancy, then that error is used to adjust the assumed flux density in the stator pole, and the entire iteration continues until the error is reduced to a tolerance value. Now let us calculate the stator pole flux in the path 1 as phi1 is equal to B suffix Sp into A suffix Sp1. We know that the formula for flux is nothing but the product of flux density multiplied by the area. So from this we are obtaining. Let the mean area of cross section of the air gap, rotor back iron, and the stator back iron be A suffix G1, A suffix RY1, and A suffix SY1 respectively. Then the flux densities in these segments are BG1 is nothing but pi by A, so pi1 divided by AG1, which is equivalent to BSP into ASP1 divided by AG1. Because we know that pi1 is expressed in the as BSP multiplied by ASP1. So we are substituting that expression. Similarly, BRY1 can be written as pi1 divided by 2ARY1. Since it is the rotor back iron, so the rotor back iron is present in the outer parts as well as the inner parts. So we have twice ARY1, which is equivalent to BSP divided by 2 into ASP1 divided by ARY1. Similarly, BSY1 will be equivalent to pi1 divided by 2ASY1, which is equivalent to BSP divided by 2 into ASP1 divided by ASY1. Here we are assuming BSP1 instead of BSP because BSP1 is equivalent to BSP. Next, let us calculate the MMF by using the following procedure. So, MMF evaluation. The MMF for each segment of the flux path is evaluated by finding the magnetic field intensities from the flux densities of the segments using the BH characteristics of the lamination material and the average length of the flux path in the segments. So, we know that MMF is nothing but it can be calculated from H and L. So, H multiplied by L will give the MMF. Let the magnetic field intensities of the stator pole, air gap, rotor back iron, and the stator back iron segments be HSP1, HG1, HRY1, and HSY1 respectively. The average lengths of the flux path 1 in the stator pole, air gap, rotor back iron, and the stator back iron are LSP1, LG1, LRY1 and LSY1 respectively. Then the Ampere's circuital law equation for this path is given by F1 is nothing but T phase into I, because the force is nothing but N multiplied by I. So that is number of turns multiplied by the current flowing through the turns. That is the total MMF. So instead of a number of turns, here we are using T phase. So T phase multiplied by I, which is equivalent to summation of H into L. So this summation can be expressed as twice of H SP1 into L SP1 plus Hg into Lg1 whole bracket plus half of this into HRY1 LRY1 plus HSY1 LSY1. If the computer right hand side is not equivalent to the applied MMF F1, then the error between them is a mark of incorrect flux densities in the various segments of the machine. The error between the applied and computed MMF can be reduced to a level that is acceptable by an iterative adjustment of stator pole flux density BSP and then recalculating all the other variables. Let the error MMF be defined as delta F1, which is equivalent to F1 minus summation H into L, which is equivalent to T phase I minus summation H into L. Then let us calculate the reluctance of the flux path. So calculation of reluctance. So from the final flux densities in the various segments of the flux path 1 and the magnetic field intensities, the reluctances are computed. So the reluctance of the stator pole segment is RSP1 will be equivalent to LSP1 divided by ASP1 into mu naught into mu R. The general formula for reluctance is nothing but L by mu into A. So the mu is nothing but split into mu naught into mu R. So which is equivalent to LSP1 divided by ASP1 into, instead of mu, we are going to replace it by means of the expressions B and H. So mu is nothing but B by H. So we are using BSP1 divided by HSP1. Now this HSP1 will be going to the numerator. So which is equivalent to HSP1 into LSP1 divided by BSP1 into ASP1. Similarly, the reluctances of the air gap, rotor back iron and the stator back iron are also calculated similar to this stator pole segment reluctance. So Rg1 is nothing but Lg1 divided by mu naught into Ag1. Since the relative permeability of the air gap is 1, here mu r is assumed as 1 here. So Ry1 will be equivalent to Hry1 into Lry1 divided by Bry1 into Ary1. Similarly, Rsy1 will be equivalent to Hsy1 into Lsy1 divided by Bsy1 into Asy1. In all these computations for the flux path, the mean length and their area of cross section are required, which we can derive in the following manner. So before going for that derivation, we have to make certain assumptions before the derivations. So those assumptions are listed below. The air gap flux lines consist of concentric arcs and straight line segments. So the flux lines enter and leave the iron normally. The third assumption is the flux lines in the stator and the rotor poles are parallel to the pole axis. Fourth one, the flux lines in the stator back iron and the rotor body are concentric. And fifth one is the windings are rectangular blocks and the stator inner pole space is only partially filled with windings. Then the sixth one is the shaft is purely non-magnetic. Next, let us calculate the aligned value of inductance. So calculation of aligned value of inductance requires a magnetic equivalent circuit. So the magnetic equivalent circuit is drawn with the help of RS, RG and RR connected in the series manner, and the RRC and RY are connected in the shunt manner. So if you have a total flux pi at this point, the total flux will be splitting into both the sides by pi by 2 and pi by 2. Now look into the table which represents the length and area of flux path at the aligned position. Now we have represented the various segments and the path length and the area of cross section of the flux paths also. So for the segment air gap, the path length is nothing but L suffix G, which is nothing but equivalent to G. Whereas the area of cross section of the flux path A suffix G is nothing but L by 2 into beta S into capital D by 2 plus beta S into D by 2 minus G, the whole bracket. Next, for the stator pole segment, the path length is L suffix S, which is equivalent to Hs plus C by 2. Whereas the area of cross section A suffix S will be equivalent to beta S into L into D by 2. Next, for the rotor core segment, the path length L suffix R will be equivalent to D by 4 minus G by 2 plus HR divided by 2 minus DSH divided by 4. Where the area of cross section of the flux path A suffix R is L into beta R into D by 2 minus G. Then for the rotor core, the path length is L suffix RC. Since it is a rotor core, so the first letter R and the second word first letter C will be combined together. So we will be getting LRC, which is equivalent to pi into D by 4 minus G by 2 plus HR divided by 2 minus DSH divided by 4, which is same as the rotor core. The only difference is it is multiplied by pi. Where the area of cross section of the flux path ARC is nothing but L into D by 2 minus G minus HR in minus DSH divided by 2. For the yoke segment, the path length is L suffix Y, which is equivalent to pi into D naught divided by 2 minus C by 2. Whereas the area of cross section of the flux path is A suffix Y is equal to beta S into L into D by 2. Now the flux path can be identified from this diagram. Since the flux lines are flowing from the north pole of the stator to the south pole, we have a flux lines flowing like this in the middle portion, whereas the outer flux lines are also flowing from the north pole to the south pole like this, and the rotor is marked in the center here. So here we have found out the flux lines as 1, 2, 3, 4, 5 and 6, etc. These are the paths where the flux paths are in the unaligned position. Next, let us calculate the inductance of the unaligned portion. Now, for calculating this, we have a certain step-by-step procedure of calculation of unaligned inductance. Now, let us look into the first step. The first step, we are going to assume an initial value for the stator pole flux density, that is BSP is first assumed. And next one, we find the stator pole flux pi SP. So after assigning the flux density, we have to assign the flux value also. And the third step is calculate the flux in the path 1 for the various machine segments and the area of cross section of various segments encountered by the flux tube 1. Now we have calculated the total flux density and the total flux, and the third step we are calculating for path 1 alone for different segments like your yoke, rotor back iron, stator back iron, etc. And we have to calculate the flux path as well as the area of cross section, and based on this we have to calculate the flux. And for the fourth step, we have to evaluate the flux density for this individual paths. So evaluate for flux densities in the various segments. Okay. Now after calculating the flux density B, then we have to draw the BH curve. So from the BH curve of the lamination material, we have to find the H for the corresponding B of the segments. And in the next step, we have to compute the length of the flux path in each segment L, because we have already found out the value of H. If the H is multiplied by L, we will be getting the MMF value. So next step, we have to calculate the length. So after calculating H and L, the next step is we have to calculate the MMF for each segment by taking the product of H and L. After finding out the MMF, we can draw the magnetic equivalent circuit. Okay. So the the magnetic equivalent circuit and write the Ampere's circuital equation. So from the Ampere's circuital equation only we can calculate the value of F1. After calculating F1 using the Ampere's circuital equation, then we have to calculate the error MMF. So compute the error MMF as delta F is equal to F minus summation H into I, and then test whether the error is within the tolerance. Tolerance is denoted by ET. Now we are going to calculate the error value and then check with the tolerance value. After checking with the tolerance, we have to find out whether it is less than or greater than or equal to. So if the error is greater than or equal to the tolerance value, then we have to adjust the value of the flux density as BSP plus or minus delta BSP, and then we have to again find out the stator pole flux and we have to proceed with the below steps. If delta F is less than ET, that is if the error is within the tolerance limit, then we are finding out the final value of BSP, and from this we are computing the reluctances and hence the inductance contributed by the flux tube 1. Likewise, compute the inductance contributed by various flux tubes. So after calculating for the first flux tube, for the remaining flux tubes also the inductances are calculated. Then we have to sum up all the inductances contributed by flux tubes to obtain the inductance of the winding. So we are getting the total inductance, and finally we are ending this procedure. The final step is we have to calculate the average torque. So the calculation of average torque is done by using dou Wm will be equivalent to Wm dash aligned minus Wm dash unaligned. For the aligned position we have calculated Wm dash. For the unaligned position also we have calculated Wm dash. So we are going to subtract these two. So from this we will be getting delta I into lambda 1 plus lambda 2 plus etc. up to half into lambda n minus half into lambda u into Ip, where Ip is nothing but a phase current, where delta I is nothing but the total phase current Ip divided by number of phases n. After calculating the average torque value, then we have drawn the characteristics between the flux linkage and the current value. So the flux linkage versus the excitation current for the aligned and the unaligned rotor positions are given below. For the unaligned position we will be getting simply a small straight line characteristics like this, whereas for the aligned position we will be getting a straight line characteristics and which reaches the final value of lambda n. So and it is varying for lambda 1, lambda 2, lambda 3, lambda 4 etc. for different values of the phase currents, and this minute differences are denoted as lambda I, where delta I will be equivalent to I phase divided by n. The average torque is given by T average is nothing but total work done per revolution the whole divided by 2 pi. So the total work done per revolution is nothing but dou Wm into Ns into Nr the whole divided by 2. So the T average is nothing but dou Wm into Ns Nr divided by 4 pi. Let us discuss about the second topic, the torque speed characteristics. So the torque developed, that is the average torque developed, but the SRM depends upon the current waveform of the SRM phase winding. So the current waveform in turn depends upon the conduction period and also the chopping details. So it also depends upon the speed also. So now we are considering a case that the conduction angle is theta is constant and the chopper duty cycle is 1. That is, it conducts continuously. We know that the duty cycle D is equal to T on divided by T. So if the T on will be equivalent to T, that is if the turn on time of the switches occurs for a whole time period, it conducts continuously. During the time period will be, the duty cycle will be 1. For low speed operating condition, the current is assumed to be almost flat shaped. So look at the flat shaped diagram. Therefore the developed torque is constant. For high speed operating condition, the current waveform gets changed and the average torque developed gets reduced. So for low speeds, it remains almost in the flat position. So the torque remains flat, and for high speeds, the torque value goes on decreasing manner. For all the values of theta, we will be getting the values of torque like this. Then the figure represents the speed torque characteristics of SRM for constant theta and constant duty cycle. So it is constant at low speeds and slightly droops as the speed increases. Similarly for the duty cycle also, when the speed increases, the torque value remains almost constant for low speeds, and after high speeds are achieved, the torque value goes on decreasing for different values of the duty cycles. For other constant values of theta, the family of curves for the same duty cycle is shown in the figure. So these characteristics are nothing but torque versus speed for different values of conduction angle and torque versus speed for different values of duty cycle. It's torque speed capability curve. Maximum torque developed in a motor and the maximum power that can be transferred are usually restricted by the mechanical subsystem design parameters. For a given conduction angle, the torque can be varied by varying the duty cycle of the chopper. However, the maximum torque developed is restricted to a defined value based on mechanical consideration. Now this is the torque speed characteristics of switched reluctance motor, and here we have three different regions, AB, BC and CD. The portion AB represents the constant torque region, and in this region only the duty cycle alone is varied, and this is achieved by controlling the switching on of the choppers. And in this portion the theta is maintained as a constant value, whereas the portion BC represents a constant power region. So if we have a constant power, P is nothing but omega into T, so the T omega will also be a constant, whereas in this case the theta is varied. And next let us look into the last portion CD, in which the theta is reaching a maximum value and T omega square is maintained as a constant, and the D portion ends with a maximum value of omega, and this maximum value is a permissible value. Let us detailedly discuss about the torque speed characteristics in the next slide. At very low speeds, the torque versus speed capability curve may deviate from the flat torque characteristics. If the chopping frequency is limited, or if the bandwidth of the current regulator is limited, it is difficult to limit the current without the help of self EMF of the motor, and the current reference may have to be reduced. If very low windage and core loss permit the chopper losses to be increased, so that with a higher current a higher torque is obtained. Under intermittent conditions of the force, very much higher torque can be obtained in any part of the speed range up to the base speed omega b. So the motor current limits the torque below the base speed. The corner point or the base speed omega b is the highest speed at which the maximum current can be supplied at the rated voltage with fixed firing angles. If these angles are still kept fixed, the maximum torque at the rated voltage decreases with the speed squared, that is T omega squared. But if the conduction angle is increased, that is theta on is decreased, there is a considerable speed range over which the maximum current can still be forced into the motor. So this maintains the torque at a higher level to maintain constant power characteristics. But the core losses and the winding losses increases with the speed. Thus the curve BC represents the maximum permissible torque at each speed without exceeding the maximum permissible power transfer. This region is obtained by varying theta suffix d to its maximum value theta suffix d max, where theta suffix d is the dwell angle of the main switching devices in each phase. Point C corresponds to the maximum permissible power, maximum permissible conduction angle theta d max, and the duty cycle of the chopper is unity. Curve CD represents T omega square constant. The conduction angle is kept maximum and the duty cycle is maximum by maintaining T omega square constant. So the point D corresponds to maximum omega permissible. The region between the curves ABCD and the x-axis is the permissible region of operation of the SRM. That is this ABCD, and this portion is the permissible region of operation of SRM. Now let us look into the third topic, methods of rotor position sensing. Now, while looking at the methods of rotor position sensing, it mainly depends upon the current sensing methods. So, first we are calculating the current measurement for feedback control, and this involves two different methods. One is a direct method and another one is an indirect method. In the direct method, we have two types, with galvanic isolation and without galvanic isolation we can measure the current. So, with galvanic isolation, it is based on the Hall effect method, and without galvanic isolation it is a resistor based method, and with Hall effect method is expensive, whereas the resistor based method is of low cost or least expensive. Whereas when coming to the indirect method, we have a sensing the voltage drop across the drain source of a MOSFET. So this is done to measure the current value. It is truly sensorless and there is no additional expenses also. Now let us look into the current sensing. So the current sensing methods. So the current control could be inexpensively achieved both with sensors and without sensors. A number of options emerged as indicated in the flow diagram shown in the above figure. So the direct measurement with galvanic isolated current transducer is expensive solution. So non-inductive low ohmic resistors can be used to monitor the current by measuring the voltage drop across them. So they are not galvanically isolated, as in many applications galvanic isolation is not a strict requirement. So this method provides the most accurate current measurement with the least amount of investment in the materials and processing circuitry. But it introduces an external resistor component in the circuit which consumes the power in the order of watts or less amount of power. So the indirect method, such as the one utilizing the resistive nature of the drain to source conduction path of a MOSFET, is used, whereas for monitoring the current we have an attractive alternative. It also requires additional components to serve as a transducer, as the phase power switches could be used for monitoring indirectly the currents. So the special MOSFETs called SenseFETs are available with processed current signals that minimize additional control electronic circuitry to transform the drain to source conduction voltage drop to the control level and keep it isolated during its off state from the control circuit. Otherwise, the drain voltage at the turn off will be at least equal to the DC source voltage, which is multiple times greater than the control supply voltage and will damage the control circuitry. Now let us finally discuss about the current sensing with resistors. So two different implementations of resistor based current measurements are possible. Only one resistor could be used in the path from all the bottom switches to the negative DC rail. Say for example asymmetric converter as shown in this figure. The phase current measurement is not available with this implementation during freewheeling of a phase. So more or less an average current can be obtained with this setup. If the two phases are simultaneously conducting, then it is not possible to separate each phase current in this method. Therefore, it will be useful when no overlapping conduction occurs in the machine phases and the average current control is acceptable. In the second arrangement, each phase current is sensed independently with one sensor as shown in the below figure. With the help of the series resistor RS1, we are sensing the current. Including the resistor in the freewheeling path allows the monitoring of phase currents continuously except when the current is being turned off or commutated once and for all at the end. Now in the circuit diagram we have 6 semiconductor switches with 6 freewheeling diodes. So the semiconductor switches in the upper limb are represented as T1, T3, T5, and in the lower limb are T2, T4 and T6. Whereas the freewheeling diodes are represented as D1, D3 and D5. And similarly for the negative phase, the freewheeling diodes are D2, D4 and D6, and we have a series. For energizing the phase winding A, the switches T1 and T2 should be in the closed condition. When the rotor position sensor sends a command to turn off the switches will be turned off. So the energy stored in D will be fed back to the supply through the freewheeling diodes D1 and D2 through the S1 to the supply itself. So the current flows through S1, and from this the current sensing resistor we are extracting the current value, and the entire circuits operates. And similarly the other phase windings B and C will also operate based on this method, and this is a very suitable method used for measuring the currents, and from this the rotor position sensor can be accurately measured. Thank you.